so here we go. My life was a snowman, and this is about neutrinos. So I thought a good introduction to neutrinos would be an excerpt from John Updike's poem, Cosmic Doll. Neutrinos, they are very small, in fact, point like in the standard model. They have no charge and little mass, and hardly interact at all. They're just a silly ball, that's obviously true. To them, to which they simply pass like dust rays down a drafting hall, although that is really indicative of weak interaction cross sections, and there isn't a practical method of detecting neutrinos. Or photons from a sheet of glass, and you can see he was clearly foreshadowing electron theory, so this is why particle physicists are rarely asked to critique poetry journals. The first appearance of neutrinos, or lack thereof, comes from a puzzle in the 1930s that in a number of sort of nuclei, a neutron will occasionally sort of decay, and we go to two sort of visible particles. You see there, it sort of goes to a sort of slightly lower mass proton and electron. And if this is all that's happening, it's a two-body decay. The energies are perfectly determined, and so you should know exactly what the energy of the electron is. But when that energy was measured, what was found instead was a spectrum. And so what was found instead was sort of a spectrum of energies, all less than what the predicted energy of the electron should have been. And this led Wolfgang and colleague to then postulate that maybe there's another particle, one that you cannot detect, which escapes and carries away some of the energy with that. Nowadays, of course, we know that the neutrino fits within the standard model like this. So you have the quarks, you have the leptons. There are three different types of neutrinos. Anyone that's taken particle physics course, so there are like 6 quarks and sort of 6 leptons in the sort of structure. Do you remember why the leptons mirror the same structure as the quarks? It's worth asking. Nobody knows. So if someone in Academy answered, I would have jotted down and published it, gotten another prize. So it's worth trying. It's one of the things that points to something maybe beyond the standard model. There's some clearly deeper symmetry hidden here. We don't really understand it. Another thing we don't understand now is the neutrinos. We now know, which will be, what this talk is about, is that they have mass and that they mix with each other. And none of these is predicted by the standard model. In fact, mass, the fact that there's mass, is definitely sort of outside of that. There's something else that's outside the standard model. I sort of said this is sort of the picture of the universe. Of course, it isn't. There's a dark side of the universe as well, dark matter, dark energy, and we don't understand what any of that is either. So the standard model these days is looking a little worse for wear, and we know there's something beyond it. We know that this has to come down, but it's been very hard to get there through accelerator physics. The LHC was built, I guess it found the Higgs, which is part of the standard model. The hope was there would be very clear evidence of something beyond the standard model, and that's proving very difficult. Neutrinos are impossible to way through the wall, right? So this is the interest that is currently. The observation neutrino mass is the only laboratory accessible physics definitely beyond the standard model. And so we're using this to sort of chip away at things. Doing neutrino physics is tricky. As you know, if you go ahead and try to compute what a typical interaction length is for a neutrino produced by the nuclear decay, you get a very large number, which can be expressed in other units, something like sort of several light years. If you try to make this interactive, you can make a detector out of lead or something like this. So it seems a totally impossible task right from the start. So the only way you can actually detect neutrinos is to play a numbers game. You have to sort of look for very intense sources of neutrinos, build as large of an experiment as you can manage in a quiet place, and every now and again, by just dumb luck, you'll get interactions. And that's the only thing you can do. So one place you can go when lots of neutrinos produced is the sun. You have to go there, the sun's sort of right there. All the sort of fusion reactions sort of do this, and it has to do with how the sun produces energy. There's an interesting history about how the sun produces energy, and debates about that go back some time. So back in 1862, Lord Kelvin didn't know how the sun worked, but sort of reckoned that it must be down to somehow converting the gravitational potential energy. And so from that, he deduced the age of the sun to be about 20 million years. So this bothered another person at that time who had a sort of crazy origin, sort of theory of evolution. And he needed slightly longer for this sort of theory to work. And he just analyzed the erosion of the soil in the Weald in the south of England and sort of said, well, the Earth alone has to be at least 300 So being the good scientist that Kelvin was, he called Darwin an idiot. And being the good scientist that Darwin was, he said, okay, maybe I'll leave this argument out of the second edition of my book. So what they could have known, of course, is that there's a totally different energy production mechanism in the sun, which is nuclear fusion. And so, because of this, it turns out that evolution can work, aside from certain parts of Kansas, but that's another story. And what happens at the very beginning, at the top of the chain, comes down to sort of the protons, because right, the stars are beginning like sort of mostly hydrogen. And protons don't want to come together, they want to repel each other. But under the sort of intense pressures of the sun, and with lots and lots of them around, now and again you can get them to come together and undergo a weak interaction where it's essentially the opposite of sort of beta decay, where now you're forcing basically turning the neutron sort of back into turning the proton into a neutron, emitting a positron and an electron neutrino. And this is a process that kind of kicks things off. There's another process that happens. It would be useful if this. Oh, there we go. Oh, good. There's another process that happens at a sort of slower, at a smaller contribution, sort of PEP thing. But this is sort of the main one. And because of that difficulty of making that reaction work, that's the thing that kind of keeps the genie in the bottle, right? If it wasn't so difficult for this to happen, stars would just go, and that would be it. But because this process is slow, it kind of keeps everything sort of in check. And then you start building up heavier and heavier elements from this. And along the way, you produce neutrinos. And always electron neutrinos. That's the only thing that can be produced in the sun. So the first measurement of this was a very ambitious experiment by Ray Davis in the Homestake mine. And he used this sort of several hundred tons of cleaning fluid. This is perchloroethylene, and it was the chlorine that he was interested in. And you can get neutrinos interacting with chlorine, producing radioactive isotope of argon-37, which is a noble gas you can flush out of the system and bottle up and take away to a lab and count them radioactively. You look for that thing to decay, and you can then sort of see how many, how we're sort of doing this. This was really a groundbreaking experiment. It took a lot of people a long time to get their heads around it. This is one of the first of these chemical experiments where this is you think of all the sort of trillions and trillions of atoms inside of there, and Ray was measuring something like half an atom a day being converted to this, right? It seems completely impossible to do that. And but you realize it's sort of an efficiency game. You don't have to be able to collect everything out of there. You just have to know what your efficiency of a collection is. You count over a longer period of time, you can do this. But it was scrutinized for a while. He won the Nobel Prize in 2002 for this, for the first sort of real measurement of neutrinos from the sun. But what he found was a bit odd. He found fewer neutrinos than he had expected. And subsequent to that, a number of other solar neutrino experiments were done. So this is a plot from 1998 where theoretical predictions for these different classes of experiments that were all looking at these different types of interactions. The top of the colored bars represent theoretical predictions of what these experiments should see, and all these experiments saw less than expected, something like a third to a half of the expected number of electron neutrinos. And so this started to become more and more of a problem. So this became known as the solar neutrino problem. And the solar neutrino problem had a few obvious solutions to it. One is that experiments are wrong, because especially back then, famously, you could, a colleague of mine once said, no one ever lost money betting neutrino experiments wrong. That was certainly true back then. There were a lot of spurious observations and things. But I just showed you there were 5 different experiments over the course of sort of number of years, using 3 different techniques. So this doesn't seem to be the answer. Another possibility was, we don't understand the reaction cross sections, either the production mechanisms in the sun, exactly right, or the detection sort of cross sections. But over the years, all the important cross sections were measured. Another good one, and sort of leading was, the standard solar model is wrong because astronomers, come on, factor of 10 you're doing well. To sort of say you can get things with a factor of 2 or 3. But all this is again, calculations not only sort of checked, but measurements of interesting things were made of the sun that kind of battened things down, that sort of didn't allow much wiggle room. for example, measuring vibrational modes of the sun. You can sort of see the sun oscillate, and this actually helped constrain energy transport within the sun, and that helped constrain the types of reactions going on to a very high degree. So that seemed to be the answer. So the final answer, so possibility was new physics. It's sort of new physics. See what I did there? What if the sun can only produce electron neutrinos, but what if somehow, on the way here, they change into one of the other types of neutrinos, and these experiments were never designed to detect? So it's a good trick to get away with it. Now, history is never really linear. Certain things happen at once. And while this was bubbling away, there was another phenomenon that was observed. It was initially thought to be, again, some you can understand the experiment, you can understand cross-section, something like that, of neutrinos from a different source and of a different kind. So these had to do with neutrinos from atmospheric interaction. So up above us, sort of, something like 5 kilometers or something, but all around sort of the atmosphere, there are interactions with cosmic rays with the atmosphere. These are mostly protons and some heavier things. And they come in, and when they interact, they tend to produce pions. So those sort of in the third year course, this is the easiest thing to produce. You sort of fragment stuff at these energies, you get pions out. The pions decay to photons, to gamma rays, so they're boring. The charged pions undergo the following series of decays. So you have sort of pionized decay to an anti-muon neutrino and a muon, and then the muon travels a bit, and then it undergoes a subsequent decay to an electron, a muon neutrino, and an anti-electron neutrino. So these are all sort of conserving lepton numbers, or our family sort of flavor numbers, you sort of see there. And then the charged pion undergoes sort of a similar sort of series of decays, sort of on this side. So with this sort of simplistic model, then you sort of see that for every electron neutrino you produce sort of 2 muon type neutrinos. And a number of underground experiments that had the ability to have some to distinguish these sort of two didn't seem to see the right ratio compared to sort of prediction. The experiment that finally sort of gave had a strong, sort of nailed what was sort of happening was a supercamiotomy experiment. So this is this large water turn-off detector in Japan, about 20 kilotons of water in that sort of volume was sort of filled, and they could sort of see these interactions. They're able to point back where the direction the interactions came from. And so they could actually sort of plot the ratio, this sort of number of electron neutrinos and number of muon neutrinos, as a function of sort of azimuth angle, or sort of distance to the point of production. And what they saw sort of looked like this. If you look the events that looked like electron neutrinos, that looked fine. They didn't change at all. But the muon neutrinos disappeared as a function of sort of the zenith angle. So this is the first good indication that neutrinos have mass. So you don't know what's happening. You don't know why they're disappearing or what the mechanism is. But they are changing state. They're changing somehow as a function of distance, which means the neutrinos have some kind of sense of time. Right? The more time goes on, the more they change and do something else. And so the reason this tells you they have mass is particles that are massless, traveling at the speed of light, they have no sense of time. Okay? So the fact that these are changing tells you that they are traveling slower than the speed of light, just even a little bit. Therefore, they have a sense of time, and you sort of see this go on. So this was the first indication that neutrinos have mass. And as I sort of said, that is not described in the standard model. So you can get to a possible conjecture for that what was going on. I can explain this in solar neutrinos as well. Is that what if what we call the electron neutrino actually exists as a mixture of different mass states? So this is a very sort of bizarre quantum mechanical thing, where it's a sort of business that if you ask what is the mass of an electron neutrino, it's not defined. It's a probabilistic mixture of masses. And if you ask, okay, for this massive neutrino, what flavor is it? That's also not defined. So you define this sort of a mixture. So it's a strange phenomenon. Mixing of sort of quarks in certain similar contexts sort of has been seen. So in order for this to work, again, neutrinos have to have mass, but it looks like they may have mass. So very quickly again in the third year course, you'll probably sort of see in the derivation And I'll just sort of mention sort of quickly that if you simply describe, say, simple two-component mixing model, you say the electron neutrino with some mixture of mass state 1 and mass state 2, and you have a muon being the orthogonal combination. Or I can also sort of turn that around and sort of say the mass states are therefore these mixtures of the flavor states. And then you let them propagate with time and distance, like a plane wave, right? So you sort of stick this out in front of it and let that sort of move along. Then you can show straightforwardly that if you start with, for example, things such that you have purely an electron neutrino, and then you let it sort of propagate along, you'll end up with it sort of oscillating. That when you try to measure the electron neutrino, then it seems to sort of change depending on the distance and the energy that you have. So this is kind of the result of the fact that neutrinos are produced as flavor states, but they kind of propagate as mass states. And because of this mixing, you have this sort of strange phenomenon. But I can show you this because I brought a couple of neutrinos with me. We can think the right. Oh, there we go. Yeah. I'm smiling because neutrinos are your friends. So here's a situation where these neutrinos are completely sort of decoupled from each other. So they each have their own sort of basic ground state energy, and that's sort of like their mass, and they don't care about each other. So if we now sort of say that what we have is a neutrino which exists as a mixture, so I have a quantum mechanical mixing device here, which I will apply. So now we have a coupled system. Then what happens is we start something that sort of looks purely like this, and if I just sort of wait with time, you'll see this will completely sort of come to a stop, and all the energy will sort of be over here. And if I wait, it will go sort of back and forth and back and forth. And interestingly, the mathematics describe this almost exactly the same mathematics. And so that's what's going on. So that would be what you sort of think maybe that explains then the solid neutrino problem. We now know, in fact, that is probably almost certainly, well, we definitely know that is not what's going on. But something close to it is going on. There is an additional thing that happens in the sun. One of the problems with this sort of oscillation model is you have to kind of fine-tune the mass differences in order to get the oscillation sort of work out exactly right. And with the measurements that have been made, you almost needed almost exactly one perfect oscillation link between the sun and the Earth. And even then, it didn't quite get the data. So something else was sort of happening. And basically it comes about to the fact that in coming through the sun, the bit of the neutrino that is electron-like can feel the other neutrinos around it, the other electrons around it, right? Because there are plenty of sort of electrons in the sun. And that electron density sort of gives you an effective, changes the effective potential. And it gives you sort of an effective mass, if you will. The part of the electron neutrino kind of feels heavier because that's to sort of work its way through these other electrons, essentially. And so as a result, you can have this resonance condition that is some sort of change in density, and you can all of a sudden hit this magic density where you very efficiently sort of swap the neutrinos over to the other sort of mass state. And essentially this is what's going on. So neutrinos that emerge from the sun are in a different mixture than you would sort of think. And then they sort of come to us. So it changes that oscillation formula. Okay. Certainly at the time, you can't keep good theorists down, no matter how many times you shoot them. So there's never any one model for these sort of things. So especially at the time, there are lots of different possibilities. You're having an electron neutrino, but where's it oscillating to? How is it sort of oscillating? There's lots sort of different possibilities here, including sort of this possibility of a sterile neutrino that doesn't interact with anything, so you can never sort of detect it. I've tried to change the nomenclature of this because I thought that should be called a neutrino. But for some reason this hasn't quite caught on. Anyway, so you have to do an experiment to really decide what is really happening here. What to sort of say is that model really sort of correct and exactly what are the components of that model and rule out these other sort of things. So the guy that came up with the way for doing this is Herb Chen. So he was my first PhD advisor. And an absolute genius. He sadly died of leukemia when he was only 45, and so we never got to see the resolution of all this. But it was really his idea for the SNO experiment. The SNO stands for Sudbury Neutrino Observatory. Yeah, just the nicest guy and just, you know, one of the most brilliant physicists I ever met. So really, this is a real tribute to him, how this is all panned out. So this formed the sort of the SNO collaboration, which was about half a dozen institutions from Canada, half a dozen from the US, and then at the time it was sort of just us in Oxford. And because of sort of her, we ended up in Sudbury, Ontario, in Canada. And so this is sort of a picture of where Sudbury is. It's actually around the same latitude as us here, but it's significantly sort of colder. So there is sort of Sudbury. And if you haven't made your holiday plans yet, by the way, I just want to put in a plug for Sudbury. It has a lot of really interesting sort of tourist attractions. There's the Superstack, which is the largest freestanding chimney in the world. So that's good. There's also, of course, there's the Big Nickel, which is it's a big nickel. And there's fine cuisine, tidbits. It's really particularly there. Anyway, there's and find and really sort of nice recreation spots like Meatbird Beach. So this is my daughter when sort of early on in the experiment. So she used to come with me to the collaboration meetings, and during a number of the feisty collaborations, she's definitely the best behaved person there. This is my all-time favorite postcard from Sudbury. Sudbury, the red hot slag pouring is a Sudbury landmark. So that would grab you, kind of book. So why we were there? For two reasons. One, it's a mining town. It's the Superstacks and distributing things, so there isn't as much acid rain falling around. And it's one of the deepest mines in North America. We needed to be deep underground to get away from cosmic radiation and stuff that could interfere with the measurement. The other thing is that Canada has the largest sort of world supply of heavy water, which we needed for our experiment from their Canada reactor program. And so we borrowed a kiloton of heavy water, which had to be escorted in tanker car by tanker car. We had to pay, so we could not purchase this. We sort of simply loaned it to us or stored it, and we paid something like $1 million a year for insurance on this. So this kind of already sort of sets the scale. So this was in the central volume of the largest acrylic vessel at the time that was ever built, so 12 meters in diameter. It was surrounded by 7 kilotons of very pure normal water, and this acted as shielding against radiation coming in. So the whole point about this is you have all this sort of shielding, so that the middle of the detector is incredibly clean, nothing can sort of come in and interfere. And when we detected light that was produced in there by something like about 10,000 photomultiplier tubes that were arranged on this sort of geodesic structure. The reason we used heavy water was the following. You get access to 3 different types of reactions, the top two particularly important for us. You have a charge current interaction where the neutron joins with just a bounce state of neutron or proton. And so you can come in and change the neutron to a proton and get an electron out, and then that gives off light, and that's what you sort of see. And that's the diagram for this. So you only sort of detect electron neutrinos in this process. And it also sort of turns out that the electron that comes out, these are heavy compared to the electron, right? So almost all the kinetic energy goes into that. And measuring the electron, we do a very good energy map of the neutrino. Then you have neutral current interaction, where anything can come in and just bust up the deuteron into its constituents. And so the idea is if you can detect the neutron, you sort of see that something like that has happened. The trick is that not only can this do this, but anything can do it. Gamma rays can do this. Anything above 2.2 MeV of energy can bust up the deuteron. And so you have to make the detector incredibly radioactively pure, right? So you have to get the water clean to something like a part 10 to the 15th of uranium and thorium in the water. Something like down a mine, which isn't the cleanest of places, and less than like a teaspoon of mine dust would have basically wiped out the signal. So it was very challenging. And then this other sort of reaction, which was less important for us, but important in the scheme of things, was basically this elastic scattering off of the electron, and you can sort of get this. And this is mostly sensitive to electron neutrinos, but there's a little bit of sensitivity to the other type. But the bread and butter has to do with this, that by measuring this interaction, you sort of see all the neutrinos produced by the sun, regardless of their flavor. And then you can sort of see how much, if any, change from electron neutrinos. So we don't call it snow for nothing. This is sort of winter in Sudbury. So never live in a place where you have to plug your car in when you go into the shop to kind of keep the engine going. And this is the mine shaft. So the number 9 shaft goes down. It's about 2 kilometers underground. So it's about a 10-minute ride, depending on who's driving the car. And when you get down there to the snow site, then you have about a 20-minute walk. At the bottom, it sort of looks like this. So it's an active mine, very sort of prosperous mine, in fact, sort of like nickel and copper and other sort of precious metals, lower ones that are produced down there. But you go down there with everyone else, all sort of suited up, and then you walk through the mine to get to the experimental area. The entrance to the experimental area sort of looked like this. And you're about to cross from this kind of environment to really an ultra clean environment. And so the first thing you do is sort of clean off your boots, okay? But then you go through a change of clothing, you go through showers, and you emerge in really a high-tech underground laboratory that's really suited. Sorry, that's the one next door. Ours looks more like this. And so it really is sort of very sort of clean. There are lots of sort of bits here that try to sort of keep down dust and all that, and you sort of walk around. And you notice that aside from bits of electronics and things like that, we have a lot of plumbing and a lot of sort of systems just to kind of keep the water pure. We had to purify these large scales of liquids, and then you had to figure out how to test that they were really pure at that level, right? So you had to assay these things to incredibly sort of accurate levels. And so this sort of goes on for a bit. The cartoon picture of the detector looks sort of simple, but the construction was certainly sort of complicated. And this is sort of the mine, sort of as things were, before things were being put in. This is this geodesic structure being pre-assembled in California before it was shipped off piece by piece. And everything had to be reassembled underground under these very sort of clean conditions. So they're just being reassembled sort of underground. This is the acrylic vessel was made of something like 225 different tiles, which had to be rebonded, had to be bonded underground for this big area. These jigs sort of held these tiles in place, and this was a real pain. No one had ever done this before, and this delayed the experiment by a significant amount, because it had to be, this thing had to be bonded to a very precise level to make sure that it contained the heavy water, that there wouldn't be any fractures or anything like that. There's another sort of there's a view, and then phototubes have been sort of populated around here with dust sheets on the inside. Here's another view of the edge of sort of that acrylic vessel. So the acrylic vessel is about that thick, and it's sort of huge, so it has almost the aspect ratio of like a soap bubble. We think that one of the consequences of this is if you go into aquariums these days, you know how you can do these things where you sort of walk underneath and you sort of see all that sort of stuff. It used to be that the joints had these like metal bands around them. They don't do that anymore. And we think it's because they learned from us how to do it, how to sort of get these bonds right. I wanted to ask when I joined the experiments, what happens if it leaks, right? Because the heavy water is very precious. I was assured that they don't these calculations there. You can't leak. You can only catastrophically fail. So then there are these concentrators. This is one of the contributions from Oxford. These increased the light driving power of each of the phototubes by a fair bit. And then this is like a fisheye camera view from the inside as things are sort of buttoned up. And there's what the experiment looked like. Then obviously before we sort of filled with water. And so we did this, and we sort of removed the sort of floating floor, and we filled it with water, and we turned on the electronics, and as the water hit the bottom of the detector, it was like fireworks. There was electrical breakdown happening everywhere. It turns out that the waterproof connectors on the back of the phototubes weren't. So I've dug this out from the archive when all this was happening, and we could sort of see that as we emerged from the water to retard bacterial growth and that kind of thing. We also remove nitrogen just because we do, we don't have to. And so maybe there's like a partial pressure difference in nitrogen, which is exacerbating this. We could put nitrogen back in. No one will talk about this. The experiment is totally divided. People sort of said, I don't understand this, it doesn't make any sense. So we sort of say, no, we said, well, try it, we have to try anything. Anyway, when we were having a debate, we sort of flipped the switch, put the nitrogen back in, and the breakdown stopped. So, I'm not a religious person. But if I did one thing, this was a bloody miracle that this sort of happened, and it saved it, and the experiment was absolutely fine after that. It was more than fine. It behaved better than our expectations in terms of its sort of how beautiful sort of signals look, how clean things look. What we saw in the detector is sort of this. The charged particle goes through, it produces this ring of Cherenkov radiation, and so it forms this sort of nice ring from the amount of light you see that tells you something about the energy. From looking at the timing of the hit, you can triangulate where that electron occurred. And for this event, it happened in the middle of the detector. There's nothing coming in or out. This is a very strong candidate of a real solar neutrino sort of event. And so we can reconstruct the position of the event, and we reconstruct the direction from where the ring is pointing, the energy, and something about the whether more particles are being produced or whether things are scattering around, and we can say something about that. So when we did our sort of signal extraction, this is from one of our papers that came out. You can sort of see that our raw data sort of looked like it was measured here, and our analysis concluded that it was a composition of charge current events, neutral current events, and elastic scattering events. You see they have different sort of energy distributions. We have some uncertainty on them, and that was our background. This is above this sort of threshold 5 MeV. That's crazy. That sort of good. We anticipated we'd have a lot more background on this, and this is almost pure sort of measurement of the neutrinos. So it's hugely successful. We made sort of papers as far and wide as Wolverhampton. So we were very pleased about that. And at the time also, people probably certainly don't remember, but there was before sort of the internet TV and things like this, there was CFAX. Does anybody sort of heard of CFAX? So we actually made it to the science and technology pages of BBC CFAX. So there we go, missing solar particle mystery. So this is page 6 of 6. Okay, so we weren't the top story, but still, we did this. You may want to know what the top stories were. So here's one of these. People could soon make home fizzy fruit, and another was Russian pop group reaches for the stars. So we were really sort of buoyed up by this sort of thing. So we made our sort of first measurement, which I'll come back to in a sort of moment, and then we did the experiment again, but by adding salt. This isn't exactly how we added salt, but we added salt to the water, and the reason for that was to enhance the neutral current signal. So this really sort of makes sure that you can sort of separate things particularly well. The idea is you produce this sort of neutron, you need to capture it. Chlorine-35 has a pretty good capture cross-section for neutrons. And it goes to this excited state, chlorine-36, and it gives off photons. You can see that really, very easily. So we did that. And then we ran with that for a little while. And then we did the experiment again. This time we took out the salt, and we added these neutral current detectors. These are specifically designed sort of helium-3 tubes, very high purity, especially produce copper. Took many years to sort of perfect this. And these we had to now anchor into the detector in various sort of places while it was filled without accessing the detector. And so this was the process for doing that, where it was guided down and attached using a remotely operated submarine, ROV. And that sounds very James Bond, and I love sort of saying that, but the fact is it kind of looked like a floating toilet. The tubes sort of placed down here, but it had cameras on it, and then these were detected, and we sort of totally did this. So we had several different phases of operation, and lots of ways to explain the data, but here's one which is kind of nice. If you decompose the neutrino flavors in terms of the ones that are electron-like and the ones that are other, mu1 tau neutrino-like. This is what you sort of see. The standard solar model would say you have all electron trike neutrinos and the flux is here. This is what the flux is of, this is where the point should be. Our first measurement, which is only sensitive to electron neutrinos, so it only gives you a constraint sort of in this direction, not in that direction. And so it looked like this. So this already tells you there's something different, there's something else that's going on here. We compared this with the elastic scattering measurement, so this is what we did in the first paper, that had already been made by the super Conley experiment. Because it had a little bit of sensitivity to the other types of neutrinos, it gives you a slightly slanted constraint, which is there. And the fact that this intersection is not there tells you, yes, you're seeing neutrino oscillation. You're seeing flavor conversion, you're sort of seeing other flavors sort of existing there. Then we can do that again with our own measurement of the elastic scattering of electrons. And then we can look at our neutral current measurement, which gives you a 45 degrees sort of slanted sort of thing. These axes are distorted, so it sort of looks like this. And then we did it with the salts, and then we did it with those neutral current detectors. And so this experiment had an incredible degree of redundancy. And from this you could then, and that's what the standard solar model would have predicted, and we can sort of see that the standard solar model is right. All the right numbers of neutrinos are produced, that the neutrinos are changing flavor, and you can sort of set constraints on this. But the really interesting thing about this experiment, there's just no doubt, this experiment just, absolutely no doubt, there's no question this is what's going on by a series of cross checks. So it's turned out to be really beautiful. The experiment ran until November 2006, when the high voltage was sort of wrapped down for the last time and it sort of ceased operation. It's an active mine, and the following day there was a rock burst, one of the largest that had been recorded around there. Detector's fine, but it did produce a shock wave inside the detector sufficient to crush a number of the neutral current detectors there. So there you go. You should always end with a bang. And so that was the bang it sort of ended on. And so that was where things were until 2015, when this happened. Oops, sorry. Let me go back and see if I can increase the volume on this.
Neutrinos are very basic subatomic particles that we don't know how to subdivide any further. And okay, they're asking me to dumb it down a little bit. A subatomic particle is smaller than an atom. Atom is a unit of matter. You don't know what matter is? Okay, neutrinos are like Timbits. Chocolate, sometimes they're like cherry filled, and sometimes they're like the old-fashioned glazed. I must be the first person that ever won a Nobel Prize in Timbits.
Fabulous. So Art was the international spokesperson for the project, I think it's sort of Canadian head. And the number of people the laureate can take long to the ceremonies in Stockholm was sort of quite limited. Nevertheless, Oxford made such an enormous contribution that myself and two other colleagues here got to attend. So this was pretty cool. So Stockholm, for those who haven't been, is sort of very sort of pretty city. It was a great sort of time of year to be there. This is a bit of the sort of the Old Town area, and they really rolled out the carpet because I found this shop when I was walking around. It's not just sort of the ceremony. It's not just sort of this is a series of a week or two where things sort of happen. And during Nobel, where it's really sort of relentless, certainly for the laureates. So there's a Nobel lectures, and there are radio appearances and panel shows and all this sort of thing that goes on. There's a Nobel concert. This is a particularly successful photo bombing I was very proud of. And then there's of course there is the Nobel banquet, which is really something to be seen. The cutlery and all the plates and everything are sort of special, but only used for the Nobel banquet. And it's all televised. And so before they bring out each plate, the audience at home sort of sees the chef talking about how we create this plate, like a master chef sort of thing, and then have decorated. Here's how it's produced, and then you see them bring them out and sort of serve them to everybody. So I asked one of the servers, I was like, "This is televised. This is national TV watching people eat dinner, and occasionally you'll have little blurbs talking about neutrinos or parasitic worms or something like this." I said, "How many people watch this?" And she said, "Oh yeah, at least 1 million." Out of like a population of like 9 million. That's fabulous. That's just really great. So here's our hobnobbing with the princess. And then after the banquet, I think what's the best part is there is something called the Nobel Nightcap, which is a sort of party that's put on by students from all over Sweden. It's hosted at the University of Stockholm, but they plan this throughout the year. They have a couple weeks to kind of execute and sort of set everything up. And so when we all got these, and then for the students themselves to attend, they have lottery. So only very few of them ever get to sort of see this. But the guests of the Nobel Prize winners, sort of, and the laureates themselves, get to sort of visit. And this guest book sort of lists all the visual map of all the different rooms and a description of the different sort of themes and things that are going on here. And so this is here's the Aztec temple room, and then this was done up to look like a train car. And so this is probably the only time I've seen me in white tie in the library. This is Nick Jelly, who's now retired, but he was one of the colleagues here at Oxford. He says that's lobster beast. His eyes were glazing over, I'm not so sure. It was a fabulous thing to do. It was also very strange. We were very aware of this because this is a handful of us that were there. And the collaboration over the course of the experiment, maybe a couple hundred people sort of worked on it. Just at Oxford alone, we had other academics and we had students and postdocs. That was sort of gone through, and of course the workshop. And we were very aware of, we were in no way sort of representative of the effort that we couldn't have done this without all this sort of work. And we were also aware of the element of sort of chance of how lucky you have to be selected for a Nobel Prize in the first place. There's an element of randomness. It's not perfect, how things are awarded. But for a couple of weeks, Sweden kind of stops everything and do their very best to sort of celebrate, academic achievement, this sort of thing, which is just marvelous. It's really wonderful. I also couldn't bring my daughter, who was sort of a bit older at this time. But I did bring her back this really nice hat from Sweden. And you can see from the expression on her face, that was enough. Following the ceremony, the first place that art stopped by was here in Oxford, because of the contributions he stayed over in Mansfield. I picked him up very bleary-eyed in the morning. He was going nonstop. But we had our own sort of Nobel banquet, and we were able to invite back a lot of sort of students and the department. That was sort of really nice. Of course, this isn't the end of it. And it was also sort of weird because, we'd done that, the big moment really was when we published, when we sort of found the result. And so this was a nice way of sort of capping things off. But things sort of keep going. There are still more questions. So here are a few questions among them regarding neutrinos. So we said neutrinos are all left-handed. Why are they left-handed? We just parameterized that. We stuck them in the standard model and said they're left-handed, but why is that? What's the mass order of neutrino states? We label these mass states, say the flavor states are mixtures of these mass states. We label 1, 2, and 3, but we don't exactly know which of those states is heaviest, for example. And then what's the absolute mass? The neutrino oscillation, what that tells you is the mass differences between them, but we don't know what the absolute mass scale is of the neutrinos. Why are the masses so small? They are like 1,000,000 times smaller than the smallest mass anywhere else in the standard model, like 1,000,000 times smaller than the electron. So something's going on here. And how did they get mass in the first place? Right, I've alluded to this before. You think mass should say, oh, we discovered the Higgs. It's the Higgs mechanism. The Higgs mechanism is particularly coupling between right and left-handed states of particles. But neutrinos only have left-handed states, so it doesn't work. So you either have to postulate that there are right-handed states, for which there's no evidence we haven't sort of seen, or you have to postulate that there is some other coupling going on, some other mass mechanism. And the fact that neutrinos are so much different, they seem to sort of stand apart in mass from the other particles, it's suggesting there's something else happening there. The difference between neutrinos and neutrinos are left-handed, antineutrinos are right-handed. Is that the only difference between them? We don't know of any of the quantum numbers that sort of distinguish them. And then, to what extent do neutrinos violate other symmetries in nature? We know that the fact they're left-handed, they violate parity constantly, which is this sort of symmetry where left and right-handed should be the same. But in our universe, it's left-handed for the weak interaction. And there are other symmetries that are very important that perhaps start to shed light on what happened in the stages of the early universe. Okay, over the years, a particular paradigm is developed, which more or less drives neutrino physics these days. And there are odd things that people look for, obviously, but this is one of the driving sort of forces. It tries to meld a number of these things together, and its framework looks like it could explain a number of other things as well. So here's the basic picture. In the beginning, the fundamental states of forms of neutrinos, fundamental fields of neutrinos, is such that we have right and left-handed neutrinos and antineutrinos, and like all good fundamental sort of states, these are masses. These are sort of permanents before they attain any sort of mass. Now we're going to give them a mass through a Higgs-like mechanism. All right. Now, a tenet of the standard model is that lepton number, the number of leptons minus the number of anti-leptons, is conserved in all interactions. There's no evidence for this. This is purely an assumption. Okay. There is no theoretical principle that says this has to be the case. So let's assume that it isn't the case. And let's assume the way we're going to give this mass in this sort of that there's a Higgs-like field, and these states will interact with that field. And if it is blind to lepton number, these states can mix. So they undergo a mixing. And a good analogy for this, I don't know if some of the theory it seems like K-naught mixing. There's something like a K-naught and K-naught bar, and it turns out because strangeness is not conserved in weak interactions, they can mix and you get this K-short and K-long state. And they're really mixtures of the particle and antiparticle states. Basically the same thing happens here. So you get these sort of mixtures, and you end up with what we sort of observe to be a right-handed neutrino. I'll come back to that in a moment. But really it's a mixture of these more fundamental sort of fields, and what we call a left-handed neutrino. And it is a mixture of these sort of fields. Now, because it's gone through these mixing, those mass states these sort of states of neutrinos are not independent of each other. If I change the mixing of one, it changes what happens to the other. So why don't we observe right-handed neutrinos, these right-handed neutrinos? Well, let's make it so you can't observe them by making that mass really large. An interesting mass scale is the grand unified scale. So this looks to maybe bring together some other things. It turns out that if you make that of a grand unified scale, you naturally suppress the left-handed neutrinos to the sub-eV scale, which is where we observe them. So that's very pretty. So this now would explain the mass scale of neutrinos, and it gives you a link into grand unification. So you have these heavy right-handed neutrinos in the early universe that are so heavy, grand unification scale is ridiculously large, they're not going to hang around, they're going to decay. So maybe you can solve another problem in the universe, which is why do we exist? We have to create both equal amounts of matter and antimatter initially, but then that should have annihilated, there should be nothing left. Somehow an asymmetry is developed, that some of the matter has, antimatter is swapped into matter just a little bit, for that bit to survive and make the rest of everything. We don't know how that happened, but we know certain conditions called the Sakharov conditions that you must have in order to make that happen. One of them is you have to have something called CP violation. And this allows things to develop this asymmetry when they undergo decay. We can see CP violation in the quarks, in sort of normal hadronic interactions, but it's not large enough, it doesn't explain it. So maybe this is where it happens. In that case, this undergoes decay, the decay predominantly to matter. So this gives you leptonic matter. Now you have to get this back into the quarks as well. It turns out that you don't have to do anything else. At these huge mass scales, these huge serenities, there's something bizarre called Speyleron solutions, which allow you to cross over. This basically has to do with tunneling between vacuum states of leptons and quarks. It's in the standard model. So if you've got this set up, this just happens. And then you've got the universe. So there's leptogenesis. This is that's what it's called. It's a very pretty picture, right? It really surprised you. We have no idea if this is right. We see sort of hints. There's certainly more ways of doing this. There's sort of theme and variations around these sort of things that happen. But there are certain predictions that are there. One of them is that the neutrinos exist as these mixture states of, more fundamental particle and antiparticle and this is what I call the Majorana neutrinos. So essentially, if I take that neutrino and I charge conjugate it, I turn it into its antiparticle, it's just the right-handed mixture of exactly the same fields. So in other words, the neutrino would be exactly the same as its antiparticle, just mirror flipped. So if that's the case, and if they have mass, so imagine you have a neutrino going around like they're sort of left-handed. So let's say you have a neutrino going around left-handed like this. That's its projecting helicity. If it's traveling less than the speed of light because it has mass, then in principle, I can boost to a frame where I see it going the other way, and now it looks right-handed. And so you can sort of translate that into a transition probability. So there would be the possibility, if there's nothing else that distinguishes neutrinos, that you could sort of flip from one to the other. So how do you look for this? Again, because of the lightness of neutrino mass, it is incredibly difficult. Probably the only way we know that you can get direct access to this is through a process called double beta decay. So single beta decay looks like this, right? This is sort of the neutron turning into a proton, and this W, and then you sort of have this sort of going on. It was recognized back in 1935 by Maria Doppelmayr that there are some nuclei for which single beta decay is energetically forbidden, but double beta decay is happening as a single quantum of that, two at the same time, is allowed. This comes from like the pairing term and in the semi-empirical mass formula for those that are familiar with that. And then this basic sort of character, this sort of standard model, sort of simple sort of thing, was first sort of then experimentally observed in sort of 1988. Couple years after Doppelmayr, Ettore Majorana sort of realized that if it was possible for neutrinos to be Majorana particles, that if they were their own antiparticle, if they could be flipped, then occasionally you get this process going on, where basically one flips the other is absorbed internally by this internal line, and so you don't have neutrinos emitted, you have neutrinoless double beta decay. The characteristic observation of that is that you are not losing any energy, like you started with normal beta decay. So at the endpoint, all of it is there, right? So this happens. So the signature for this is you have the chromosomal double beta decay, but now and again you will have things really getting to the very endpoint, and that's what you want to see. I should stress that this game is incredibly hard. This is one of the hardest sort of experimental sort of questions in particle physics. There are at least a dozen different efforts underway. Your ability to see this very much depends on what the neutrino masses are, which we don't know, we have bounds on, and what the ordering of the masses are. It may be that the next generation experiments will not have the sensitivity to sort of see this phenomenon. But the only thing you do is go look, because there are a lot of different models in which you could see it. And along the way, you develop the experimental techniques that will then enable future experiments to gain the sensitivity to be able to see it. So it is a long-term goal. It is much harder than what we sort of saw with neutrinos. The particular experimental technique that we're pursuing here, and with a number of universities, other universities, is going back to the SNO detector, with an experiment called SNO+, but it is looking at sort of different things. In this case, we take this, so this is a nice sort of picture of it from a photo of it from sort of inside the cavity. You can see this sort of acrylic vessel. And in this case, it's sort of filled with water, but what we're about to do is fill it with this stuff called liquid scintillator. So this oil-based sort of substance that gives off light very readily when particles go through it, and lets us go to lower energies. So we can see as a result, we can look at a number of different things, but including double beta decay. The way we sort of do that is by loading one of these isotopes that can undergo this sort of process into the scintillator itself. And we have a huge volume, and so we can put a lot of it in and do this sort of sensitive probe. Tellurium-130 turns out to be a very nice isotope. It has a very high natural abundance, so you have to do expensive enrichment. And so if you can crack how to do this, it gives you the possibility for really being able to just load more and more and more and really sort of getting higher sensitivity. There's a trick you have to figure out how to get it in. And we figured out one method of doing that here, which involves making this sort of organic complex, which then dissolves mixes into the liquid scintillator. And so there's a lot of, and so Oxford has really been at the heart of driving a lot of this, and you'll see me a number of days sort of down in the sort of tinkering with chemistry, trying to sort of make improvements to this. So it isn't just sort of running in the same sort of system. We've inherited that infrastructure. We've had to do significant modifications to that. And along with the plumbing that was there before, we have a lot more plumbing now for this purification of the scintillator itself, and a lot of other components that go into this. And so this has been a sort of very difficult undertaking, and a number of other sort of subsystems for purifying the tellurium and then creating this sort of organic complex that goes in. This is sort of the tellurium that's sort of underground at the moment. The project has had a number of setbacks, just like SNO has had a number of setbacks in sort of doing this. Constructing the scintillator plant has been a real pain. We are now just on the edge of things. We are now sort of, we have this water phase. We're starting to put in the liquid scintillator, and then next year we'll start doing the loading for the tellurium and begin looking for this process. And again, we believe that this first step, we can sort of show that this technique works as we believe, that we can really then increase the loading. We have a good shot at sort of going for this. So it just sort of goes on. It's sort of difficult, and I just said there's a number of setbacks, just as there were in SNO. But I think probably my experience is that those kind of, you just have to go in and do battle, and it's the ones the experiments you have to do battle with that are probably the ones that are most worth doing. So as things go on, this talk can't, and so I'll just sort of end by indicating that I'm still snowing. Okay. And thank you very much.
When are you anticipating some more results?
So We have results. So the nice thing about the project, even though we don't know if we'll be able to sort of see delta beta decay in the first sort of instance of this, we can do a lot of other things. There aren't that many, but we can sort of see these and look for an oscillation of these as well. There is a previous measurement of an oscillation, but there are there's a sudden discrepant result between two different methods of doing this. We should be able to resolve that within a year of data, and so that actually is an interesting result. We can look at neutrinos, antineutrinos from the Earth, genoneutrinos, and this is really about heating models of the Earth. But there are some interesting uncertainties about that. A similar measurement was made by the Camland experiment in Japan. The interesting thing about us is we're in a very different geological part of the Earth with very well understood geology, especially with all the mining that's going on there. And by comparing the two, we can start to separate the contribution from the mantle and the crust and start to get an idea of these sort of things. So I think, there's lots of these sort of things coming, and we're just at the beginning of that.
You said that whether or not you were able to detect it was sort of dependent on what the actual neutrino masses are.
Yeah.
So what proportion of that range are you sensitive to?
Range is sort of a difficult sort of thing. We know, how do you put this? There are these two possibilities. There is a possibility we know that two of the masses are close together and one of them is farther apart. We don't know if this is like this or like this. This is the so-called, let me get this sort of straight. This is the so-called normal and inverted hierarchy. This would be better for us. It would mean that the part of the neutrino that is electron, that couples for delta beta decay, is higher and that's easier to detect. There are hints that that may not be the case, maybe the other way around. Even if it's the other way around, it's possible we can detect it because this absolute mass scale is not known. And it could be the neutrinos are degenerate. It could be that they are all sitting right around the same mass with just sort of little difference between them. If that's the case, discovery can happen any time. So there's just a lot of, so basically there's sort of a lot of uncertainty about that. If you are pessimistic, you sort of say it's the wrong hierarchy and the lowest neutrino mass is really very, very low in mass, then you need an experiment, and there's nothing, and it also depends on your model for what the coupling, for what's producing the masses is, then you need an experiment that may be, at least an order of magnitude more sensitive in terms of this, maybe more. Figuring out how you make that economically, how you sort of do that. There are very few techniques. I think the technique that we're working on is one of the few that could possibly do that. And so, one of the things that sort of excites me about the project is that you have all these other physics to look at. We have a shot maybe at sort of seeing this if we're fortunate. But if not, you're working on a technology that is probably the right one for the future to sort of be able to really sort of push down. I can't lay odds though.
You mentioned those sort of asymmetry between left and right hand neutrinos in the first. So would there be a way of detecting the right hand ones?
So the trick is in that model, the heavy right-hand neutrinos don't last. You never see them. So they sort of but there are certainly models. So when I mentioned these sort of sterile neutrinos, basically you can have models where you have right-handed neutrinos that are lower in energy. In the standard model, only left-handed neutrinos couple, and so you can only sort of detect those. And so you can only look for the right-handed neutrinos by kind of inference. You see them disappearing, and you don't see what they're disappearing to. You kind of rule out that they're going to something else. So there are experiments that look for these things. Occasionally there are hints of things that then go away. This sort of thing is sort of around. But it's you look for decays with missing energy that you can't explain, so people try to look for right-handed neutrinos as well.